My name is Mike Graziano, and I'm going to be explaining my work for exam 2. So for number 3, I wrote down the values of each ion, and I found the molecular weight of the ion. And to get the equivalent weight, I did the molecular weight divided by the valence, and got these values for that. And to get the equivalent weight ratio, I divided the equivalent weight of CaCO3 by the equivalent weight of the ion to get these values, and to get the milligrams per liter as of CaCO3, you multiply column 1, which is the values for each ion, by the equivalent weight ratio to get these values. For total hardness, it's Ca plus 2 plus Mg plus 2, which are these values, and I got 306.8 milligrams per liter. For carbonate hardness, it's the same as HCO3, which is 198.44 milligrams per liter. For non-carbonate hardness, it is the total hardness minus the carbonate hardness, which are these values, and it comes out to be 108.36 milligrams per liter. For the lime dosage, it's the value for CO2, which is 45.6, the value for HCO3, and Mg2 plus minus 40, and 20, which is a constant from the lecture notes, and the value I got is 285.84 milligrams per liter for the lime dosage. For the soda dosage, we need a hardness of 85 milligrams per liter, and in the lecture notes, we have to 40 milligrams per liter always stays, so we subtract 85 from 40 and get 45 milligrams per liter. And to get the soda dosage, you subtract the non-carbonate hardness minus the 45 to get 63.36 milligrams per liter. For question 4, part A, we need to find the concentration of the glutamic acid. So 147 grams of C4H9O4N has 14 grams of N in it, so the concentration would be 147 divided by 14 times 120, and the 120 comes from the N value given in the initial question, and that comes out to be 1260 milligrams per liter. For the CBOD, we take 144 divided by 147 times this value of 1260 to get this value, 1234.28. For the NBOD, we do 64 divided by 147 times the concentration of the glutamic acid to get 548.57. For the theoretical demand, or the THOD, we take the CBOD plus the NBOD, which are these values here, and it comes out to be 1782.85 milligrams per liter. For the glucose, in the question, the BOD test equals 3,000 milligrams per liter. So the oxygen demand, we take the 3,000 subtracted by 1234.28, which is from the part B, the CBOD answer, and that comes out to be 1765.72 milligrams per liter. For the CBOD, we take 192 divided by 180, which is 1.67 or 1.067 milligrams per liter. And the NBOD is 0 because there's no NBOD for glucose. The THOD is the same as the CBOD in this scenario. And the glucose concentration comes from 180 divided by 192 times the oxygen demand from the previous part, and that value is 1672.79 milligrams per liter. Question 5, the video is posted in the section. And question 6, part A, we have to find the mixing DO of the river and wastewater. So to do that, we are given these values up top, and to do that we use this equation, the DO equation here, plug in the numbers given, and get 1.938 milligrams per liter. For part B, we need to find the ultimate BOD after mixing for the river and wastewater, and we are given the BOD is 85 milligrams per liter at 15 degrees Celsius, and the K is 0.3 D to the minus 1. So to get this, we use the formula for KT, and we plug in the numbers, and it comes out to be 0.159 per day. And the LO, for the LO formula, we plug in the numbers that we previously calculated, and that comes out to be 154.99 milligrams per liter, which is the ultimate BOD. For the next part, for the deoxygenation rate, we use the formula known as LA, and we are given LW and LR in the question. So we use the formula, plug in the numbers that we've calculated and been given, and get an LA of 35.25 milligrams per liter. The next part, oh wait, I'm sorry. So part B, we were finding the ultimate BOD. Part C, we were finding the mixing ultimate BOD after mixing with the river and the wastewater. Now for the next part, part D, this is where we are calculating the deoxygenation rate, not part C. So I messed that up. But part D, for the deoxygenation rate, we are given N, V, and H, and we use the formula KD to find the amount per day at 20 degrees Celsius. Then we convert that to become 15 degrees Celsius, the KD at 15 degrees Celsius, and we plug in the numbers into the formula and get 0.170 per day at 15 degrees Celsius. For part E, we are calculating the reoxygenation rate, and we use the formula KR, which is the formula here I have written down, and we plug in the numbers from the previous parts that were given to us and get 0.326 per day at 20 degrees Celsius. And we have to change the 20 degrees Celsius to 15 degrees Celsius. So you use the same formula as before, plug in the numbers, and get 0.290 per day at 15 degrees Celsius. And for number 7, this first one is the example given in the question. The second one, plants, the energy source is sunlight, carbon dioxide is a carbon source, and I have it classified as photoautotrophs. For the next one, I have it classified as chemoautotrophs, and for the last part, I have it classified as photoheterotrophs. And that is my explanation of the questions and answers I have for Environmental Engineering Exam 2.